Hello friends, now I will discuss one important topic of active filters. You will find a lot of questions based on this topic in exam. The name of the topic is the generalized expressions, that is the generalized expressions of transfer functions of different active filters I will say simple active filters. So here we will see the generalized expressions, right? I will be talking about the second order filters only. Reason being, you have lot of questions based on second order filters, right? So first let us talk about low pass filter, right? If you remember, for first order, if you remember the first order, what was the transfer function of the filter? Hs equal to some constant in numerator divided by 1 plus s by some frequency, say that was r some if you talk about low pass, so that was 1 by rc, something like this. So I can write this something like this: some constant in the numerator divided by 1 plus bs, something like this we can say. So I am writing this a constant, I am writing this as a constant, right? So this is a first order filter. For second order filter, how to implement? We can have one low pass filter here, and we can connect another low pass filter in cascade, and so on. Higher order filter can be, or simple, there can be one second order filter, right? So for second order filter, if you remember, we had if you remember the pole zero diagram of second order low pass filter, what was that? That was simple. If you try to recall, for second order filter, for second order filter, what was there? We had only two poles located on j omega axis. That was for second order low pass. The transfer function for that can be written as something like this: AHS. When you have two poles, so numerator will be constant because there are no zeros in the system. Then you can write it like this: s square plus bs plus c. If there is quadratic term in the denominator, if there is quadratic polynomial in the denominator, so factors of this will be giving me two values of s which are nothing but poles, and factors of polynomial in numerator, that is factors of numerator, will be giving me 0. So there is no term containing s, so there is no 0 in the transfer function of second order low pass. So this is the generalized expression of transfer function of a low pass filter. Similarly, let us talk about high pass filter. In high pass filter, first of all, try to recall the first order filter, right? In first order, if you remember, the transfer function can be written like this. It was like this: some constant divided by 1 plus 1 by rc divided by s. It was something like this. So when you take LCM of this, it will be as plus 1 plus some, you can say, b into s. You can write this in terms of this, right? So here what I mean to say is, in case of first order low pass filter, we have 1 0 at the origin. What is 0? That is factors of numerator polynomial. So factors will be giving me s equal to 0 if you put equal to 0. If you put it equal to 0, that will be giving you poles. So there is one pole in the transfer function of first order low pass, and there is 1 0. But if you talk about low pass, there was only one pole in the, if you put it equal to 0, that give me one factor, that is a pole, and numerator is a constant, so it does not have any 0. So in low pass first order filter, there is one pole only located on negative real axis. In second order low pass, we have two poles, both located in left half. In first order High pass, there is 1 0 at the origin and one pole located in left half. And when you have second order filter, if you remember the transfer function, we have two poles in the numerator. In second order, you can see the transfer function of a high pass second order filter, and we have two poles, and I can write that something like this: s square plus bs plus c. So in case of second order high pass filter, we have two zeros at the origin and two poles located in left half of S plane. That is your generalized expression of transfer function of a second order low pass filter. I hope concept is clear. Now let us see third one, that is band pass. And remember, band pass filter is always a second order filter. So let us talk about band pass filter. And band pass filter can be implemented by connecting a low pass filter in cascade with a high pass filter like this, right? High pass filter, say cutoff frequency of this is low pass, so cutoff frequency of this is upper cutoff frequency, say FH1, and cutoff frequency of this is high pass, so FL1. So both will be FL and FH. So condition for this to work like a band pass filter is the cutoff frequency of low pass stage FH should be greater than the cutoff frequency of high pass stage, that is FL. So when you connect two filters in cascade, the transfer function for the filter will be simple product of the transfer function of low pass, that is 1 plus s into b, suppose, multiplied by transfer function of high pass, that is a dash, or you can say a1 b1, then a2 by a2 into s divided by 1 plus s, that is what, high pass is b1 b2 by s, you can say, right, something like this. And if it is there, you can neglect this part, right? Or you can say, if there is s in the numerator, I am sorry, if there is no, I have taken only one 0 in the numerator, so I can rewrite that part like s divided by 1 plus s into b2, because high pass has one pole 1 0 at origin and one pole on negative half, you can see that is high pass first order, and low pass it has only one pole. So this will be something like this: a 1 s plus b dash s square plus c s plus 1, something like this. Or finally what I mean to say, it has 1 0 at origin and two poles in the left half. So a band pass filter has in general, you can write simplified expression. So the transfer function of a band pass filter will be how, that will be having what, it will be having one pole 1 0 at origin, and there will be two poles located in left half of S plane. That is general expression just like this, but there is one pole. So this is when it has one pole, 2 0, when it has 1 0 2 poles, it is band pass. When it has two poles, two zeros 2 poles, 2 zeros at origin and two poles in left half, it is high pass. And when there is no 0 at origin but two poles in left half, it is low pass second order. Please see the difference. I repeat, a second order low pass has only two poles located in left half of S plane, there is no 0. Second order high pass has one, you can see that second order high pass has two poles at origin and two zeros at origin and two poles in left half of S plane. And your band pass has 1 0 at origin, that is 1 0 at origin and two poles in left half of S plane. That's what I am trying to say. Let us see the fourth one. Fourth one is what? Band reject filter, right? So in band reject filter, a band reject filter can be implemented by connecting a low pass filter and high pass filter in you can say in shunt or in at the input of an adder circuit. This is adder, right? So when you connect both of these at the input of adder like this, and input is kept common to both, right, say that is input, or we can say, we can show input to both the filters is same. This is V in, right, output is V out. So in that case, what will be the transfer function? The transfer function of this will be, Hs will be simply sum of the transfer function of these two, say that is A by 1 plus B into S, so A1 B1 plus A2 by 1 A2S by 1 plus say B2S, something like this, right. So when you have a simplified version, when you simplify this expression, finally you can get the transfer function. But rather than going into the depth and in-depth analysis of this, what I will say, and you should remember, you can refer the textbook for that, but I will say, just remember this from examination point of view. The transfer function for low pass second order filter is something like this: As plus P, that it has 1 0 and 2 poles, maybe it's like SC plus D. So it has 1 0 in the left half of S plane and 2 poles in left half of S plane. So in case of band pass, there is 0 at origin. You see the difference between this and this. In case of band pass, there is a 0 at origin, but in case of band reject, there is 0 in negative half of S plane, and there are 2 poles in both the cases. Now the last filter to be discussed is all pass filter. We will see the transfer function of all pass filter. In case of first order all pass filter, the general transfer function is one have 1 0 located in right half of S plane on positive real axis, and 1 pole located in left half of S plane on negative real axis. So on negative real axis we have 1 pole, maybe that is at minus 1 by A, and we have 1 0 in right half of S plane, maybe that is this. But remember, both are symmetrically located, means both are at equal distance from imaginary axis, and imaginary axis forms an image. In case of second order filter, the expression will be similar to this. The only difference will be something like this, maybe C minus AS plus S square and C plus AS plus S square, something like that. So in case of all pass filter, maybe we have 2 zeros on negative positive real axis and 2 poles on negative real axis, but both must be symmetrically located. Or it may be something like this: we have 2 zeros on right half of S plane, 2 poles on left half of S plane, but imaginary axis forms a mirror. Both will be mirror image. It means if it is at distance A, it will be at distance minus A, something like that. So in case of all pass filter, we have a mirror image about j omega axis with all zeros located in right half of S plane and all poles located in left half of S plane, and that finishes your filters, that is transfer function of filters. So and of course that completes the topic of filters as well. So in next video we will start with the nonlinear applications of operational amplifier. So wait for my next video. Thank you very much for watching the video.